Hello, my name is YunSeok Choi. I am a student at Songyang University. Today the paper I will introduce is Ia-Bert context-aware sarcasm detection by incorporating incongruity attention layer for incongruity feature extraction. The order to introduce is as follows. Sarcasm is a form of figurative language. It has been widely used to implicitly convey an opinion or express an offensive message. Sources negatively impact the performance of natural language processing models that are related to sentiment analysis and opinion mining. Here is example of sarcastic tweet. But general BERT is classifiers is not sufficient. It ignores the characteristic of sarcasm detection problems, which are largely context-dependent. It is important to model the interaction between the response sequence and each context. So our main contribution is first, a novel architecture for context-aware sarcasm detection using pre-trained BERT and attention mechanism. And second, a novel concept of feature extraction to obtain incongruity features from sarcastic sentences. And third, we demonstrate the performance improvement in context-aware sarcasm detection. This slide is preliminary study on the sarcasm detection task. Sarcasm detection does not have a special set of vocabulary as attribute markers. Sarcasm lies in the incongruity between the actual text and the implicit meaning it tries to convey. In this case, the response sounds sarcastic with or without the context. So next case is the response alone does not sound sarcastic but contains sarcasm after referring to the context. In the following example, I know the glass is always half empty to some people. It is hard to conclude whether the response is sarcastic without knowing the context. Therefore, modeling the interaction between the response sequence and each context is also important in identifying sarcasm. In this example, the response does not sound sarcastic with or without the context. The response uses a straightforward expression where it is explicitly stating disagreement towards others' opinions. The last case is the response alone sounds sarcastic, but in the fact non-sarcastic considering the context. A non-sarcastic sentence may sound offensive because of the topic being discussed. This type of sentences can be found in the following example. Although the sentence looks aggressive, it states a straightforward opinion towards the context and there is no sarcasm intended in the sentence. And due to this characteristic of sarcasm, it can be concluded that considering only the response to identify sarcasm is difficult. Therefore, we need a classifier architecture that considers both the response and the context. In this work, I propose a novel classifier architecture for context-aware sarcasm detection called Ia-Bert. In context-aware sarcasm detection, the input sequences consist of the context sequences and the response sequences. The context sequences is a series of conversations happened before the response sequence. To perform feature extraction on the input sequences, Ia-Bert is designed with the embedding layer and 3 attention layer. As shown in the following figure, after getting the embedding representation using pre-trained BERT, the model first extracts response-centered features and interactive context response features from the given context and response sequence. These two features are then passed into an incongruity attention layer to run their important for sarcasm prediction. The output of this layer is used to predict whether the response is sarcastic or not. In the next section, I will describe each module in more detail. The first module is the BERT shared layer, which is a pre-trained language model that can be regarded as an embedding layer. To represent each token in the context and response sequences into vector, a simple BERT invariant layer is leveraged instead of two independent BERT layers. It is considered that both context and response have the same syntactically and semantic characteristic. Suppose that R is an input response sequence and C is the context sequence. So RB and CB are the embedded representation of the response and context obtained from the BERT embedding layer, and D represent the BERT embedding dimension, and N and M denote the maximum length of the response and context sequence respectively. These initial representations of the input are then passed through some attention module to extract concurrency features. The second module is the response attention layer, which is based on the multi-head attention mechanism. It employs self-attention on the embedded representation RB to extract response-centered features. Each attention head is computed as the following formula. The attention layer takes RB as the key and query, and a scaled dot product attention is applied as the score function as it is recommended for identical attention. The weight metrics WQ, WK, WV are trainable parameters. The attention representation computed by each head are concatenated and summarized by feeding them to a linear projection layer using weight matrix WB. The next module is context response attention layer, which aims to obtain the incongruity features between context and response sequences in an interactive manner. This layer is also built using multi-head attention, and a bilinear attention score is applied as a scoring function, which is considered to be useful for features fusion. The incongruity feature in this module is viewed as a fusion of information between the context and response sequences. The module takes the embedded representation CB as the attention key and RB as the query. Each attention head is computed as the following formula. WBA is bilinear attention weight used to fuse the features for context and response sequences. In this layer, our attention head representations are also concatenated and followed by a linear transformation. The output of the context response attention layer is denoted as our CRA with the following dimension, which is the length of the response sequence, and D0 represents the output dimension. From the previous two attention layers, we obtain a response-centered feature RA and an interactive context response feature CRA. Based on the preliminary study on the task, one feature may play a more important role than the other feature depending on the case study mentioned in previous section. In the incongruity attention layer aims to perform reweighting on these two features using the training signals obtained from the correct and incorrect predictions. Instead of directly concatenate and flatten the poor representations on input for the final prediction layer, the two-layer the two features are combined and treated as an input sequence consisting of two elements. This representation is fed to a single head attention layer, which implements the scaled product attention score. The attention representation is computed in the same manner as the response attention layer, except for the number of attention heads. The related features as the output of this layer are denoted as R dot and R share dot, which represent the response-centered feature and context response feature respectively. The final prediction layer takes on as input the concatenation of these two features. The prediction layer consists of a linear layer and a softmax function to determine the probability of each class in Sarcasm detection. The probability is computed according to the following equation. WP is the trainable parameter and Y hat is the prediction result. A cross-entropy loss is applied as a training objective for the model optimization. Next, I will briefly describe two baseline models related to the context-aware Sarcasm detection. To leverage the pre-trained BERT model, previous work simply concatenates the context response sequence as input for the classifier. They also conduct an experiment by adding a special context-separate token to create a boundary between the response and the context sequence. The other approach uses an interactive attention network to model the interaction between a response sequence and each context. They initialize all word embedding in the context and response sequences using the glove embedding model, and they employ an RSTM network to obtain intermediate representation of each token. Then they use attention mechanism to extract interactive features between the response and the context. One module takes the response as the query, and the other module takes the context as the query. These attention features are then concatenated for prediction. The other method called BERT attention encoder network uses a similar approach as the interactive attention networks by leveraging the pre-trained BERT as embedding layer. The other BERT-based model is local context-focused BERT. During the attentive feature extraction, LCF BERT leverages multi-self-attention and employs a dynamic masking, which masks or weakens certain tokens within the specified semantic distance. For example, when the model computes the attention score of the word right, the surrounding tokens will be preserved and the rest are masked or weakened. This slide is experiment section. To train and evaluate our proposed model and the baseline models, I used the open training set from the ACL shared task on figurative language processing for context-aware sarcasm detection. The data set were collected from two online discourse platforms, Twitter and Reddit. The experiment includes several input sequence combinations. The model is trained on the response sequence and a number of utterances in the context sequence. The setting for the context sequence are last utterance, last two utterance, last three utterance, and all utterance. For context input more than one utterance, the contexts are concatenated in a reverse order to obtain the most recent utterance as the start of the context sequence. For this dataset, the proposed model Ia-Bert obtains the best performance when the response and the last two utterances are used as input, which results in 0.505 accuracy, and in the Reddit dataset, it is achieved and the model takes the last three utterances of the context sequence. In this setting, Ia-Bert obtain 0.7 accuracy. Considering a number of utterances happened before the response sequence can give relevant information about the topic under discussion, and taking the last two or three utterances appears to be effective in identifying sarcasm, while referring to the last context only or more than three can be either insufficient or less informative. The following table shows the performance comparison of the proposed model with several baseline models. Ia-Bert outperforms the baseline models in terms of accuracy and F1 score for both Twitter and Reddit dataset. Overall, the complex texture of Ia-Bert demonstrates a better performance than the baseline model. While maintaining a comparative precision, Ia-Bert constantly obtains a high record. It shows that Ia-Bert has a better sensitivity in predicting the sarcastic response. To study the importance of each attention module in Ia-Bert, an evaluation study was also conducted by evaluating the model performance when removing a certain layer or module. As shown in the following table, removing the incongruity attention layer and directly concatenate the output of the response attention and context response attention layer constantly drop the prediction accuracy. It shows that the incongruity attention layer plays an important role in improving the model performance. In the Twitter dataset, the prediction accuracy and F1 score when considering only the feature from the response attention or context response attention layer are quite similar. Also, concatenating features from the two attention modules degrades the model accuracy but improve the F1 score. And applying the incongruity attention to this feature has improved the performance. This is a qualitative analysis. In this case, Ia-Bert shows that it has a better ability in recognizing sarcastic response compared to the baseline models. As shown in the follow table, the baseline models misclassify the sarcastic sample from Twitter and Reddit dataset. The response in both samples does not sound sarcastic when the context is not considered. For example, if we simply read the sentence, "Can't watch a video of the devil magic," we may think that the devil magic is only a video title or a name of character from a movie. But after reading the context sequence, we will notice that the praise is a sarcastic way to refer to subjects being discussed. The last to conclude, in this work I propose a novel classified architecture Ia-Bert to serve the context-aware sarcasm diction platform. The model emphasized the importance of context sequence as much as the response itself to identify sarcasm, and this approach yields a performance improvement over the standard BERT classifier, and outperforms previous work on to online discourse dataset, Twitter and Reddit. And that is all for my paper presentation, and if you have any feedback or questions, I will try to answer them.